just because if they haven't seen tensor product before, right? But actually, these axioms can be reduced depending on what you like count as a more fundamental axioms. For example, we have seen, right, that or at least I state the weakness theorem that so the theorem states that if you want the time evolution to preserve the inner product of vectors, whether it's real vectors, complex vector, then the operator that correspond to the time evolution would have to be unitary. So the actual theorem is that the linearity is not even in the assumption. It's just say that, okay, any operator, and then Wigner could prove that it's either unitary or anti-unitary. We just choose unitary because those are the set that we can make continuous in time. And so in that sense, the time evolution postulate follow from the measurement postulate. Well, here, in particular, well, so the version before we have density operator, right? So the probability of getting an outcome J is just this, right? And if you want to preserve the normalization, which is a norm, just a normal vector, then you have to preserve the inner product. And then from Wigner theorem, you would get that these time evolution have to be unitary. So some axioms can depend on the other in this way. The one thing that I want to comment about, and the record left. Okay, thanks. One thing that just a little comment is that actually there's something called Gleason's theorem, apostrophe S, I guess. And this is 1957. Yeah. That actually proved that notion of the statistical operators being density metric follow from the measurement rule. In particular, if you have a function, so now I fix the notion of measurement to be related to projector. So the idea is, okay, if you have a vector space structure and a projector is related to a projector correspond to a measurement outcome in this way that, you know, if you, for example, if you sum up all the projector, you get the identity, which means no measurements, just a single outcome, and then outcome that correspond to outcomes that are distinguishable, perfectly distinguishable, so it's like exclusive, right? Correspond to projectors that are orthogonal. Then you say that, okay, let's suppose that there's some function f as a function of any possible projector. So let's say just p that give a probabilities. So it's non-negative, and then also if I sum up all the projectors that are orthogonal, then this should be 1. But of course, this function doesn't talk about just one set of orthogonal projector, right? It means that if I can define this function, I want to define this function for any set of projectors. So here is like I sum over one set of projectors, but I can have different set of like projectors that are not orthogonal to elements of these. And this doesn't even have to be continuous. But Gleason was able to prove that in dimension 3 and above, so let's say dimension of Hilbert space is 3, at least 3. So curiously, it doesn't work for a qubit. This function that gives out the probability has to be, it turns out to be continuous, and it has to be given by an object that has a property of the density operator. Yeah, and so in this sense, the assumption, the axiom about the state follows from the axiom about measurement already. And so what happens in 2 dimensions? Because, well, that seems to be like maybe the most important case that you would think of first, right? And the intuition is that, say, if I have, well, the main intuition is that is simply that in 2 dimensions there's not enough degree of freedom or not enough constraint on this function. And the picture is something like this. So if I want to fix a set of orthogonal projector, right? Let me just think of this as like 3-dimensional real vector space first. But of course, in quantum mechanics, this would be a complex dimension. Right? So let's say if I pick one projector that points in the z direction, then I can choose any orthogonal projector. So these projector, in terms of this vector, you can visualize them as choosing orthogonal set of bases, right? I mean, choosing 3 orthogonal projectors that sum to identity, and you can rotate any. You can rotate the 2 basis vector in the xy plane anywhere you want, right? And the rule that you assign probabilities to these 3 projectors have to all be consistent. So those are sort of you can imagine that those are the constraints. But if I have just 2 dimensions, so now I'm just looking at the plane, 2D plane, looking from above, then if I choose a projector in one direction, then the orthogonal projector is forced to be in the opposite direction, right? So basically, if this assign a probability p, this has to assign a probability 1 minus p. And it turns out that what happened is that, well, when you're in 2 dimensions, there's just not enough constraint. For example, then if I choose a different direction, then I can assign the probability to these 2 directions. Like in this case, I assign q anywhere that I want. It doesn't have to be continuous. So in the end, you would like assign probabilities to, I would say not direction, because to each subspace, right? Because each subspace geometrically correspond to 2 directions, opposite direction. So you have to assign probability to this infinite set of subspace that you can rotate, and they all don't have to be related in any way. Especially if you don't assume that it has to be continuous, and you can assign this probability any way you want. So this Gleason figured this out as a response to some question about hidden variable theory. So the question would be that, well, okay, so you may have heard about hidden variable theory, something like Einstein doesn't like probabilistic nature of quantum mechanics. Maybe there are other theory, more classical like, they would hope, that reproduce the statistic of quantum mechanics or something like that. So one question that we can ask is that, well, is there any other way to assign, like, is there any other theory that's kind of like quantum mechanics? So maybe this is a bit different from the question of whether they're classical hidden variable theory or not. But you can ask, like, well, what are the constraints on the theory? Say if I start build my theory from having this structure of vector space, and I want to put probabilities functions on this space, well, what kind of theory that I can build? So this would say that in 2 dimensions you are free to do anything you want, and you don't need to have, you're not forced by anything to have quantum mechanics. But it turns out if you allow the measurement to be more general, so POVM, then you can prove Gleason's theorem in 2 dimensions too. All right. Any comments so far?
Into that dimension, the function of t has been in the plane, right?
Yeah, yeah.
So what is the can be that
yes, in a sense that there's an infinite choice to choose this orthogonal set, right? In particular, right, so basically the projector would just be this, right? But if I choose this, then it forces the orthogonal one to be in the -n direction. Yeah, and the point here is that you can imagine different theory that assign probability to, yeah, so not just this set of projector, but all possible sets, all possible rotation, but in a way that's different from quantum mechanics. In other words, you cannot, in a way that you do not compute the probabilities by taking the trace with the density operator. All right. So I think it's time to talk about entanglement. Yeah, we talked about tensor product last time. So I guess let's get ourselves kind of familiar with manipulating tensor product. So last time I defined the tensor product space by the basis, right? By taking orthonormal basis from the 2 space and then take this kind of formal product together, and then if you extend the set of vectors by linearity, so by taking all linear combination, then you get a new vector space, and this is the what we would call the tensor product space. So let me just list the notation of these for this space again. Yeah, and these 2 spaces can have different dimensions, right? And the tensor product space would have the dimension that is the product of the dimension of the 2. So if you have vector, I can, of course, expand it in this product, in the tensor product basis, which I might abbreviated like this. So here I omit the tensor product symbol and just put them next to each other. And if I have a linear operator, then I can also, okay, so here I can get this from applying the identity operator, right? And then write the identity in terms of the sum of these, the outer product of this product. And the same can be done here. So I can write this in terms of matrix elements. Okay. Now I have to have four indices. JKLM, JKLM, J, well, depends on now, yeah, you can order these indices any way that you want. So maybe like this. Sorry, yeah, why don't I do it this way? And then this would just be the corresponding inner product, right? Now, and of course, this is just so this is the same thing that we already know. The notation just get more complicated because there are more indices. So you can think of these as tensor as well, as coefficients. But now you don't have to take inner product of vectors in both spaces at the same time. In the sense that, well, we remember that if I have just one space, then the inner product, I take product of two vectors from the same space. Or you can think of it as a things that take vector in the dual space, in the original Hilbert space, then produce a complex number. So it used to be that, well, every inner product is a number, it's a scalar. But I can take partial inner product as well. So for example, if I have a state in AB, I can take inner product of a vector in, say, HA. And so what's left here would be a vector in the Hilbert space B. So let's see. So if for example, if I do this with that vector, what happens? Oh, I need KL. This is what that means, right? So you take inner product of vectors that come from the same Hilbert space. And then here, if that EJ is one of the basis vector, then I get this. And the sum collapse to JL. JL, for example. J, yeah, J, there's only one J. Sorry. Yep. Okay. Thanks. now. Right. Yeah, so taking partial inner product give you vectors in the other Hilbert space, and so you can do things like taking partial trace as well. So for example, if I have an linear operator on AB and I take the trace of B, then this would simply mean that I calculate the sum of the diagonal elements, but only with the basis in B, right? So suppose let's say F. Yeah, I don't know why I do it differently here. I take in a product of vector in A, here as I do it in B. So okay, yeah. And then by using the rule of taking partial inner product, then we can see that what is left is a linear operator. It's still a linear operator, but in this case in A, for the space A. So actually from this, I can define the notion of reduced or marginal density operator or density matrix. So if I want to, let's say, only measure one of the system. So let's say I want to measure system A. The probability that I get from measure maybe some system A in orthonormal basis. Well, how would you calculate this probability? Well, it would just be the marginal probability, right, of the probability if you say measure both systems and then average over the result of other systems. So here, so now I keep the same notation that J is the index for the basis elements of Hilbert space A, and this is for Hilbert space B. Or maybe, you know, maybe we just don't do anything to the system B, but we'll see that this is equivalent in a second. So here, so if I calculate this, right? So then I just say that this is the trace of, I got one more space. Maybe just go that direction. Okay. Sorry. Okay. And then I just write out, right, that if I already have a state on AB which represented by some density operator, this would be this. Right. Since the trace is linear, I can pull the sum over k inside. So k is sum over the degree of freedom that we want to integrate out, right? We want to average over. But if fk is just another orthonormal basis, right? So this is the identity. And so that's why I said that this is the same as not measuring the system B at all. Right. But then taking the trace here is equivalent to taking the trace of A and B consequently, like in series, right? And it doesn't matter which trace you take first, right? So you can say that this is trace of A, and so I can pull this inside, and then taking the trace of B inside. And so this tells us that for any possible probability or expectation value that I want to get out of the system A, I can calculate it. I can basically just using the same rule, taking the trace of the projector against something that acts like a density operator, right? And we call this the reduced density operator for system A. So this is all the information that you need to calculate anything that only happens to system A. So maybe let's say that this is locally, this is a complete information for the system A. Complete local information about system A. Of course, this doesn't know anything about correlation of the system A with other system. So here I just mean that if you just want to make a local measurement on system A, then row A is all we need. And you can prove on your own time that this indeed is a density operator in the sense that the trace has to be 1, it has to be positive operator. All right. So now, now we want to start looking at entanglement. So basically, we are doing prep work, right? Preparation work to more easily talk about things like teleportation, superdense coding, or Bell's inequality related to verifying or measuring entanglement or non-locality between two parties. So there is one important basis for JFSB for when these are both qubit. Yeah, so I should just say, well, entanglement between two qubits. And I guess next week, so here, let's say at least here, the HANSB doesn't have to be qubit system, right? It can have any, but at least here, since there are just two parties, so these are called like bipartite system. In general, you can think of entanglement between any number of systems, multipartite entanglement, but then the kind of subject or some analytic result is just very hard to come by if you have more than two. And well, by limiting yourself to just qubits to make things easier. So this is the simplest case that we can talk about. some non-trivial, wonderful phenomena of entanglement. So here, so I can take, so over there, I take the basis of the joint Hilbert space to be the tensor product of basis vector of each space, right? But I can also take an orthogonal basis that composed of entangled states. And the most famous one are the Bell states. And why the Bell state is spatial is sort of related to why Pauli matrices are spatial, but we'll see that later. So, so there's a Wikipedia notation. It's a common one, which I would not remember if I haven't prepared. So phi plus minus is when I have superposition of parity zero state. So when the two qubits here have the same value, right? And then the psi here just corresponding to the psi over there. And then you have the odd parity state. So this even parity is odd parity. Where I have a linear combination of 0, 1, and 1, 0. So you may recognize the psi minus state as the singlet state. 0, 1, minus 1, 0, which from the point of view of the theory of angular momentum that you learn in Quantum 101, that is a spatial state out of these four, right? Because that is the angular momentum, the zero state. So any simultaneous rotation on the two systems doesn't change the singlet state. It's like is invariant under rotation by the same unitary on both systems. So because for that reason, you can write like this too. So that means that in this state, when you make the same measurement on both systems, you always get perfectly anti-correlated result. The other three states are in the symmetric subspace of angular momentum 1. So here what I talk about is in like Quantum 101, right? That you learn that if I have to spin 1/2 and then I take tensor product, then it's you can write it as a direct sum. And this is the singlet state, and this is the family of triplet states, right? Although usually the triplet here, in Quantum 101, you would take actually. Yeah, in Quantum 101, you would take this basis. You would take this to be the basis of the triplet space. Which are also orthogonal, but if here I want to choose a basis, an orthogonal basis in which all the elements are entangled. Well, and here is a simple exercise to prove that these are actually entangled states, right? That basically, so if you remember the definition, right? So entangled state is a state that's not a product state, and so you just sort of have to do some kind of proof by contradiction to say that these states cannot be written in term of this kind of thing. Psi phi. And psi and phi here, I mean like a different psi and phi here. This is capital psi and phi. This is lowercase. Okay. So next, I'm gonna label this for fail states by is the value of a very special set of observable. And people who attended the quantum error correction school this weekend will see something that they already saw. Let's see. Okay. Okay, so maybe the first observation is that I can map between different Bell states by applying Pauli matrix to one of the systems, but it can be any one. Right? So, for example, if I have so usually people just prefer to define first faceless entangled state, and then call it omega to be basically whatever the dimension that you have, you just sum over the set with the same basis element and then sum uniformly sum over them, right? Well, if you want this to normalize, then you have to divide by the square root of the dimension of the whole thing. So in this case, I would say that this give many different notions. For qubit, this is the state. And then you can see that, for example, if I act on this state by z on some of the component, it would change the phase here, right? So for example, so let's, well, not for example, I'll just do it. Right? Well, I guess let me order the Bell basis in this way first. So this is of course one. So basically I will use maybe put it right here. I've used the first number here to label the parity of whether in the same head, right, you have the same state or the opposite. And then this would be the value for the phase. For example, 0, 1 here would mean that I have parity 0, but different phase, but the phase minus, but minus sign. And of course, this is just set with the same phase, but then the parity is swapped. And so now I can write, for example, that if I act on the first Bell state by z in the first component, then it would just simply be change the phase, right? And this is the same as acting on the second qubit. And then the same go for x. If you do this, then you increase the value of the parity bit. And now I can add on them with x and z too. Sorry. So I can do it in any order. We just give a different a result with different sign. Right? Suppose this is zx, and this is in the right order, is the right cyclic order. So this is I times y without the minus sign. Then okay, so what I do here would be that I flip the first bit first, right? So I get 1 0 plus 0 1, and then I 0 1, and then I get, when I apply the z operator, I will get the minus sign over here, right? Which is exactly this state. But you have to be careful that now if I want to switch the side to this, then I have to switch the order of x and z. And so to summarize here, I can say that this guy, right, you can write it like this, or switch the order here. Right, so the phase bit, the parity bit has to be where the x are, because the x operator flip one of the value of the qubits, so it change the parity. So already at this point, we can give one application of halving entanglement called super dense coding. I don't know why it's not just dense coding, but super dense. Maybe there's dense coding in classical already. And the scenario is, well, let's first think about how you might be able to use entanglement to help in communicating some message. Okay? So if I want to send one bit, does sending a qubit help at all? Do I want to send one bit? Yes, or like, is sending one qubit any better than sending one bit? Well, I guess in the deep sense, maybe there's something there, but if you, just thinking about it at face value, it doesn't really do anything, right? Because the state, at the end, what the receiver can do is that he can measure in some basis, and then he'll still receive just one bit anyway, because the result can be just up or down, right? So it doesn't help. Sending a qubit doesn't give you more sort of storage, doesn't give you more memory to send. But suppose that I have let's see who gonna be who. Maybe a list here. Right. So maybe first, Alice have a pair of entangled states. So have an entangled state like one of the Bell states. So let's say she has the omega 00 state, and then she distribute this to Bob. So but now and the claim is that if Alice the claim is that there is a way for Alice to encode 2 bits in the information and send it to Bob if she can send this half of the entangled pair to Bob at the end. And okay, so the way that you encode, okay, so Alice will encode this. She will decide first, right? So there's like 4 possibilities that she wants to send, and if she get a hold of this, or let's say that someone is already like has already prepared the Bell state, this state, maybe like some times ago, a few days ago, and today this Alice decided, okay, she wants to send some of the one of the 4 alternative of the message. What she can do, right, is that she get a hold of just half of the entangled pair, but even though she has access only to half of the entangled pair, she can change this state to any one of the 4 orthogonal Bell states. Okay? Just by acting on just her Hilbert space. And so she can encode 2 bits here. Well, maybe it's wrong to say here because now the information is kind of like distributed across the entangled state, right? And now, so encode here. And now she sent this 1 qubit to Bob. He already has the other qubits. Now, and then at the decoding stage, now Bob has 2 qubits in his possession, right? And now he can make a measurement in the Bell basis to decide which of the 4 message Alice wants to check. Yeah, and so here at the stage of encoding to decoding, Alice, we only send 1 qubit, but the crucial thing is that the sender and the receiver have to share entangled state and entangled pair beforehand. Yeah. This is called the superdense coding. So yeah, and feel free to ask any question anytime, right? So here I'm just gonna write that yeah. So sometimes people will write something like this. And the sign here means that can perform a task in place of. So this is one of the Bennett's law of entanglement. Here, by having 1 pair of maximally entangled state, some people say you have 1 E bit, this entangled bit, and then you send 1 qubit, and it does the same job as sending 2 bits. Okay. The 4 Bell states can also be written as a linear combination of product operators of the form sorry, where here I mean j can be 1 or 2 or 3, and then so this is saying that, well, actually I have to add the identity to this set too. So maybe let's say that let's change the index to a Greek index, and then say that this is 0, 1, 2, 3, right? Where sigma 0 is the identity. For example, okay, and this kind of claim is something that we can derive easily, right? It's just take some calculations, because I can take the basis of the operator space of 2 qubits to be tensor product of an arbitrary pair of Pauli matrices, right? So, and a general operator would also have terms that alpha is not equal to beta, for example. And the claim here is just that the Bell states can be written in states that are only sort of, they call it Bell diagonal, or like Pauli diagonal basis, because these alpha can are always the same. And this can be verified directly, for example, by basically just checking the coefficient of your operator in this basis, right? So let's say I have this Bell state, or really just AB, one of the 4 Bell state. I can show this by calculating all the inner product with all the possible basis element, right? But here, or you can also do it more directly. So for example, if I write this out, I just take the outer product, right? And then I get something like this. So I have the diagonal term, and then also the off diagonal term. And then I can start writing this projector in terms of Pauli operators. For example, the operator projector onto 0 state would be 1 plus C, right? Because the matrix C, right, has this eigenvalue. So if you add them together, you kill this guy, which is this guy is the 1, 1, this guy is 0, 0, right? And then now, and then also taking the tensor product with the same thing, right? And for if you have the projector onto the one state, you just change the sign here to minus sign. And then you do the calculation, and what you would get is that I guess this space is enough, it's barely enough. Okay, here I will omit the tensor product symbol out of just laziness. Yes, what you would find is that changing the base state simply just changing the sign of some of this guy plus yy minus plus plus x. Yeah, I hope this is correct. In particular, I can say that if I have one of the four base states, basically, right, this is A. And now this can sort of be can be translated to see what happens if I act on. So this now you can see that this kind of give a hint that these operators are kind of special for the base states, right? In particular, maybe we want to know what happens if we act on each base states by these 2-point correlation operator here. And to do that, it's better to just invert the relation here and then write these operators in terms of the state, in terms of the projector into the state instead. And here I will just do it. For example, well, let's okay. Okay, I guess to save time, since these four terms are always the same, I'll just write a sign. Okay. Plus, minus, plus, minus, minus, plus, plus, minus, minus. Yeah. And so now, if I want to calculate what happens, look at the result of applying this kind of two-point correlation operator to one of the Bell states, then I can simply look up I simply get it from here, right? Well, I guess it's a more direct way. Well, a more direct way would just be to apply to the use the definition of the state and apply directly and see if you get a phase, if you flip the bit, right? But here, for example, I can just see this directly, and I hope it's correct. So if I apply ZZ, right, so the projector would give the plus sign if you have one of these states, right? So in other words, it would the plus one eigenspace is the eigenspace where is defined by the first bit being 0. And then if the first bit, which tell you the parity, is 1, then you will get a minus sign. And so the eigenvalues here only depends on the parity bit A. And similarly, you can do the same with this guy. Yeah. So this, so the four Bell states are joint eigenstates of these tensor product of Pauli matrices, and the eigenvalue tells you the parity and the phase of the Bell states. And for y, you can just multiply the two equations here, right? Y. And the minus sign here, right? It's just because if I multiply xx and zc, I don't get just y, but I get minus y. Yeah, because basically I multiply x and z twice. Each multiplication give me either I or minus I depending on the order. So one application here is quantum teleportation, which is kind of opposite to super dense coding in a sense. Okay, so here I want to send an unknown quantum state psi by sending classical information, sending actually, we'll see why this is the case. Classical information. Okay, so maybe let's think about it. So here, I say that we have an unknown quantum state, meaning that Alice doesn't have a classical information that describes psi. Because if Alice already know what the states are, then one way to do is that she can just send the classical information to Bob, and then Bob recreate the state. However, if she wants to send a state without measuring the state, so maybe Alice produce some state during quantum computation, or she had someone has given her a state, but if she measure the state to find out what it is, then she will just destroy the state, right? Yeah. So like if she only has one copy, then there's no way to read out what the state is. But one thing that she can do is to do this by if you have a share entanglement with the party that want to receive the state. So the setup is this part having a pre-share entanglement. Pre-share entanglement is the same as superdense coding. But the task that we want to do is kind of the opposite, because in superdense coding, you send classical bits by sending a quantum bit. And also in that case, you send 2 bits. So here you may expect that, well, maybe if I can send this qubits, if I to send a single qubit, maybe you need something like 2 classical bits. And this is what quantum teleportation does. So, right, so let's see if the space here is enough. Yeah, let's go to that side. Maybe we don't need this. Okay, the setup here is that again, Alice and Bob has pre-share entanglement, and then Alice has state that she wants to send. So there are 3 parties now. And Bob is over here. So now suppose that Alice, so now she is in possession of 2 qubits, right? Now she make a Bell measurement. And by that here, I just mean you're making a measurement on the orthonormal basis consists of the 4 Bell states. And the claim is that, so once, since there are 4 possible results, right? Then Alice will, well, let's see. So Alice will have 2 classical bits over here, and then which she can telephone and call Bob here. And the claim is that once Bob get the 2 bits from Alice, then he can do something to recover the state psi, but on his side. Okay, so here, so how to verify this? Okay. So at first, how I'm gonna order the tensor product. Yeah, so what we want to really calculate is a partial inner product, right? That if I have a state psi and the state here, the Bell state here. So maybe, well, here, so how, I don't know how we want to label this thing. So maybe this is Alice, this is Bob, and then there's something in between. And Alice want to make a Bell measurement, so which would correspond to projecting onto one of the outcome, right? Projecting onto the Bell state, AB, and this is the middle oh, this is AC, right? So you make a measurement on the top 2 systems. So now I can write this as I already, oh, there's still the pink corner. I can write this, let's see. So since I use the bra here, I have to switch. And I want to do this with, I want to pull out Pauli in the system A. So system C is fine. Right. So if I take the dagger, I just switch the order there, right? AB. Right. So here I'm just rewriting this Bell state. Oh, sorry. 0, 0. Yeah. 0, 0. Yeah. Okay. So what do we do now? Well, so at first I can just sort of write this properly. So now it's the same thing, but I just transfer this to the system A. Right? System. And then I have the same Bell state on the other side. Let's see. But I can write this guy now. This is just one of the okay, so I can write this as this sum, right? EJ where well, to label the qubit properly, maybe I just write, yeah, JJ, and then J is 0, 1, right? So if I write this here, then now I can separate separate how this Bell state acts on the system A and the system C. Right? So here, right. So for the system A, I would have here, which is now just a scalar. And then the leftover J will go and act on this. So this is system C, and this is for BC. Yes, CB, right? Well, and actually I can do the same on this side too, right? Well, I guess okay. And so if I write out the whole thing again, I have this inner product, and then J here acts on the first system here and produce the Kronecker delta, right? So I have delta JK here, then the K here. And this is for Bob systems. So now J and K has to be the same. J, that's K, right? J. Then I have that IB in the state for Bob qubits, IB in the state A with this coefficient. So the ket here is in Bob's Hilbert space. Originally, these inner products come from Alice Hilbert space, but since it's scalar, now it doesn't matter. It's not really in any Hilbert space, right? It's just a complex coefficient. And say for convenience or for notational convenience, if I write this as a new state, right, psi prime, or or maybe just to be more explicit, this psi prime that depends on AB, then this would just simply be the state vector of this state, right? Because here, if I do it, if I go backward, I want to expand this in the orthonormal basis J. I will just multiply by the identity, right? And then this is what you get. Okay, and so at that point, which color I want to use? At this point, Bob receive so with probability 1/4, because here the 1/2 here is the square root of the probability. So with uniform probability, you receive one of these 4 alternative states. For a particular value of A and B, which for Bob to know which one, Alice has to call Bob. say and tells about which bit that she received when measuring in the Bell basis. But now once Bob know what A and B are, Bob know that this is the state, right? Even though he doesn't know psi, but if he want to get psi, then he just apply the inverse of these two Pauli to get psi. And so teleportation is complete. Right? And for this, so say having one bit of pre-share entanglement, so one Bell pair, and then plus 2 classical bit can do the same as sending 1 qubit. Right. Okay, and this precisely noon. So yes, I think we can leave it here. Next week, next week I will talk more about non-locality and stuff like that. Like Bell's inequality. But yeah, if you have any question here, we can discuss. ที่จริงโอเคอันนี้เพราะมันวิธีที่ผมทำนะแต่ว่าผมเคยทำแต่ว่าถ้าใช้จริงๆใช้ไอ้นี่ก็น่าจะได้เป็นจากโอเปอเรเตอร์หรือว่าอาจจะต้องแต่คิดว่าถ้าทำอีกวิธีมันยังไงมันจะง่ายที่สุดเดี๋ยวนะถ้าไม่แตกเป็นซัมตรงนี้มันจะทำยังไงได้บ้างถ้าผมว่าอันนี้มันอยู่คนละระบบนะไม่งั้นก็จะแบบ take trace แล้วก็ให้เป็น counter เปิดวิธีวิกิพีเดียมันยังไงนะมันเขียน
วิกิพีเดียมันเขียนตัวสเตทให้อยู่ในรูปเดียวสเตท
มันเป็นสเตทของอะไรของ A B C คือ
สเตทเนี่ยเศษเป็นตัว C เลยถ้าเราจะให้ผิดนะที่ผมเคยทำ
คือเขียนเบลของ A กับ C ใช่ไหม
ใช่แล้วก็คราวนี้มันก็จะรูปเป็นรูป